Howdy, welcome to Computer Graphics Crash Course. In this video, we're going to cover 5 topics: vectors, matrices, transformations that you can do with these matrices, the WebGL Pipeline, and shaders. So first, let's talk about vectors. A vector represents direction and magnitude. In 3D, we would use the components x, y, and z. There's a number of operations we'd like to do. First is addition, where we just add the components together and we get a vector out. Subtraction, similar to addition. Negation, where we take the negative, so negative x, negative y, negative z. Scalar multiplication, where we multiply each component by a single scalar value. The dot product, so we pairwise multiply the components and add them together. The cross product, which we'll define in a short bit. The length, which we'll also define in a bit. And the norm, which is the same vector but with a length of 1. Now, we're going to talk about matrices soon. However, you cannot multiply a 4x4 matrix with a 3x1 vector. So the solution to this problem is to use homogeneous coordinates. Homogeneous coordinates, essentially we add one extra component, w, which we often set to 1, and we perform a projection where we divide the w component by the other ones. So x over w, y over w, z over w. So first, we want to look at the dot product. The dot product of two vectors, a and b, is equal to their components, ax times bx plus ay times by and az times bz. One of the most useful things that the dot product gives us is the cosine of the angle between the two vectors. So let's just say that a is a vector and b is a vector, and we want to find out the angle between the two. If a has a length of 1 and b has a length of 1, then a dot b is equal to the cosine of that angle. Now, it's useful to know what the length of a vector is. So, if we want to find the length of a vector, all that we have to do is simply take the square root of the dot product of itself. Now, a unit vector is essentially a length of 1 for the normal. And if we want to make a unit vector, all we have to do is divide its components by its length. So let's just say that the length of b is some constant c. Then we can convert b into a unit vector by just dividing the x, y, and z components by the length. So now let's talk about the cross product. The easiest way to do this is if we have our vector x, y, z, we can go ahead and just simply pairwise start with the next component. So we're going to figure out what the x, so if we have a cross b, we start out with ay times bz minus az times by. Next, we'll have az, because z comes after y, times bx subtracted by ax times bz. And you'll notice that the inside pairs are the same. Finally, with z, x and y come next. So we'll have ax times by minus AY times BX. The big thing that the cross product gives us is a vector that's perpendicular to the vectors. So if we had our x and y axis, that would give us the direction of our z-axis. We use this very important operation to tell us what direction our triangles face in 3D. So if we had a triangle here, we can find out what direction it is by taking the vertices and taking the cross product. So the normal would be B minus A cross C minus A. So next we're going to talk about matrices. Now we're going to use this matrix where we just use the letters of the alphabet as the column and row elements, and we want to multiply by a 4x1 vector. And we're going to see why we need to use a 4x1 vector in just a bit. So in order to do this calculation, we will need to take the row on the matrix and multiply it by the column. So what this is going to look like is AX plus BY plus CZ plus DW. And we're going to do the same for the rest of the rows, or this result. Now, there's a different way of thinking about a matrix where we're talking about the normal types of operations like translation, rotation, or scaling, which we're going to talk about in the next slide. But we also need to talk about what kinds of operations that we need to do or support in order to use matrices effectively in 3D graphics. One way is that we can think of a matrix as really nothing different than a vector. So we can do addition, subtraction, negation. Now, scalar multiplication. However, some of the other operations are a little bit different. For example, multiplication's a little bit different. We don't have a length, but we would need to take the determinant. And we'd also need to find out what the inverse is. Now, we mentioned that there's a different way to think about a matrix. And one of the most effective ways to think about it is a orientation in space. And since we're using right-handed arithmetic, this means that our columns will represent the direction of the axes. So if we can think about this, the u-axis is like the x-axis. The v-axis is like our y-axis, the vertical axis. And finally, the w-axis is like the z component. And everything is located here at the origin, which is the fourth column. What this also means is that our matrix can be divided into 4 quadrants. First of all, you have a rotation, translation, and finally that fourth row. So let's see what happens when we apply this multiplication to a regular vector. So let's just say we have m times v, where our vector v is x, y, z, 1. In other words, we will just let the w component equals 1, because projection-wise, we know that this would project to the exact same vector x, y, z. So what we end up having is ux times x plus vx times y plus wx times z plus ox. Same thing for the following few rows. uy times x plus vy times y plus wy times z plus oy. uz times x plus vz times y plus wz times z plus oz, and 0, 0, 0, 1 times xyz 1 will just give us 1. So you see that the w element remains the same. Now, if you'll observe, we will see that we basically multiplied a 3 by 3 rotation matrix by our coordinates, and then we separately added the origin, which is not affected by the location of the 3D position. So now we can go ahead and continue and talk about transformations, which we briefly mentioned in the previous slide. So the first transformation is the scaling. And the scaling matrix looks like Sx, almost looks like the identity matrix, except that the diagonal components are the scaling factor. So we will see that what ends up happening here is that we will have Sx times x, and then we'll have Sy times y, and Sz times z, and our w component stays as 1. Next, translation. So we want to move our point. So this one is got the translation coordinate all the way on the farthermost column, and the identity matrix is the rotation part. So what ends up happening here is we have x, y, z plus tx, ty, and you can see that all this matrix does is just shift the 3D position. Then we have rotation, and this one I'll leave it up to you to look up, but suffice it to say there is a form that allows us to just simply say the axis of rotation and the angle. Sometimes it's called the angle axis formula. And this will have the effect of rotating a 3D point about the origin in space. The next thing that we need to know about transformations is that we go right to left. So what that means is that if we have a world matrix This takes us from local coordinate space or model space to world space. In other words, where is it located at in the 3D world? Local space might be where is an object, where are the vertices in relation to the object's origin. Okay, then next we'll have a camera matrix. And a camera matrix takes us from world space to view space. In other words, we're going to shift everything in the world around the origin of the camera, and that's essentially how we look in our scene. We just basically move everything to the location of the camera. And we actually do this using an inverse matrix. And the inverse matrix has the property that if you multiply M times itself, you get the identity matrix. In other words, nothing happens. Okay? But if, which is the case, right? If we have a camera matrix, we'll call it C, and we take its inverse and multiply it by its world matrix, then we just get the identity matrix. But let's just say that we have the camera matrix. We're using the inverse, and we multiply it by the world matrix of another object. Then this will move W into C's space. All right? And lastly, we have a projection matrix. And we should probably give these names. So we'll call this one W, we'll call this one V, and we'll call this one P. So if we want to find out what the final position of a coordinate, like say we're taking a triangle, we want to find out where we're going to end up drawing on the screen, we will multiply P times V times W, and then let's just say that V is sub I is our coordinate. Okay, that's our position, and we can just go ahead and say that VI prime equals that result. But what's going to happen is that the V sub I is going to move into world space with this multiplication, and then it's going to move into camera space with this multiplication, and then it's going to move into projection space with this final one. And in fact, it's sometimes common just to use one matrix, say M equals P times V times W, and this calculation, it's called concatenation. It's the same idea. All right, and remember it goes right to left. For example, if we have a coordinate and we want to move it, so if we have this following series of matrices, what this means is that we're going to translate first, then we're going to rotate, then we're going to scale. And that's how that works. So now let's talk about the projection matrix, because we haven't talked about that. We talked about scaling, we talked about translation, and we talked about rotation. But we want to do 3D graphics. In other words, we want to take objects from more or less an orthographic projection, and we'd like to make it look, 3D. In other words, we want that foreshortening to happen. So one particular matrix is called a perspective matrix, and it takes a few parameters. The first of all, we want the field of view in the Y direction. We want the aspect ratio of the screen, so 16:9 if you're doing HD graphics. We want the near plane, in other words, how close can objects get to the camera before we clip them, and how far away can they get before we clip them. So the formula for this particular matrix is, we'll just call this M perspective. We need to calculate this value F. So we'll say that F equals the cotangent of the field of view over 2. Now, if the angle is, say, 90 degrees, then F equals 1. In other words, we don't do any kind of stretching with the angle of view. Okay? So we first have this value F divided by the aspect. And then go zeros for the rest of this first row. And then the Y is going to be just the stretching for the viewport, and zeros for the remaining row. And then next, we're going to do something interesting. We're going to take the Z far value and subtract or add the Z near, and then do Z near minus Z far. And then this last column here is 2 times Z far times Z near over near minus far. This is the special element here. This -1 is going to effectively move the Z coordinate into the W component. Okay? So if we were to multiply this perspective, then ignoring the X, X, Y, and Z, you'll see that this last component is going to get -Z. And what's going to end up happening is that when we do the projection, we're going to end up, remember the projection is we're going to end up dividing by the Z coordinate. And that's essentially how we go from 3D to 2D. Okay? So 3D to 2D is divide by Z. And the way that we do this is with this matrix, which moves the Z component into the W component. And then what will end up happening with the Z component is it's going to get mapped to a set of values that is appropriate for the depth buffer, which we're expecting numbers between 0 and 1. And that'll be part of the exercise that you will complete with this lesson. So now we go to our fourth topic, which is the WebGL pipeline. Everything in WebGL has to be done the correct way or you don't get graphics, essentially. Okay? And so this is kind of a checklist of items that we need to have in place so that we can go ahead and do graphics in WebGL. So one of the first things that we need is a program. And we're going to talk about these in the last section, okay? But a program consists of a vertex shader and a fragment shader. A fragment shader, fragment is just essentially used to talk about the pixel. Sometimes you've heard the word pixel shader. Fragment shader is the same idea. Then we'll have memory buffers, which are called array buffers, because we are going to store an array of vertices. Next, we're going to have the vertex array itself. In other words, we're going to tell OpenGL how the memory buffer is laid out. Optionally, we can set up our uniform variables, and these are applicable to the shaders. And we may have to set up texture maps if we're sending in textures. We may need to set up a frame buffer if we're rendering two textures. Otherwise, we don't. And then we'll need to apply state. And state can be, what is the depth test? Or are we using blending? And so on. Now, on the HTML and JavaScript side, essentially the order is we're going to create a canvas. We're going to create the context. And then we can go ahead and request an animation frame. Which is our basic thing. We would like to draw a new frame, and we want to do this as many times as we can. Okay. Later on in the course, we'll talk about some of the classes that we're going to use. So these are part of the what I call the libxor library, and we're going to have some math classes. So matrix 4, vector 3, a render config, the rendering context, which is just going to be called graphics, and an index geometry mesh. Excuse me, a texture map for loading images, and we're going to have a scene graph library, which we're going to use to request objects, 3D objects, which uses the alias wavefront type object class. So this brings us to our last topic for today, which is shaders. And essentially what we have is we have a program spelled that wrong, and it's going to consist of a vertex shader and a fragment shader. And the process essentially is we need to load a vertex shader, or we can embed one in. Then we're going to compile it. Then we're going to check if it compiled, which is called check the compile status. Then we're going to start doing the same thing. We're going to load a fragment shader. compile it. Check status. Then we need to create the program. Attach the shaders. Link the program. And finally, check the link status. So let's talk a little bit more about this linking part. So in the vertex shader, we need to define what our attributes are going to be. So vertex is going to have attributes. And attributes tell the shader what is the entry point. Okay, so let's just say that we're going to have an array buffer here. And it's got our XYZ coordinates and our normals and our colors, red, green, blue, and our texture coordinates, U, V, W, or sometimes we use S, T, and Q, or S, T, and P to represent those. And we have an array of these, and this might represent vertex 0, vertex 1, all the way to however many vertices we have. It's just laid out in a giant array. So our attributes are going to tell the shader where we're coming in. Next, we have what are called varying. And these are going to be how the vertex shader communicates to the fragment shader. Okay, so in our vertex shader, we might have a line that says attribute vec3 position. And sometimes what I like to do is use a prefix, and I'll call it a position, so I know that this is an attribute. And then we might have a varying, and I'll call that V position. So then when we get to the fragment shader, we have to copy these exactly. So we'll have varying vec3 V position. And then lastly, we need to have a way of getting our final colors out and our positions. Okay, so the vertex shader is going to produce the final vertex, or where it's going to get drawn, and the vertex shader is going to generate the final color. And these actually have special names. So GL underscore position is the variable we write to, and GL underscore frag color is what we use in the vertex shader. And finally, but not least, is we have what are called uniform. And uniforms are constants for the entire shader. And you can use uniforms in the vertex shader, you can use uniform in the fragment shader. These are things that don't change over the entire type of object that you're drawing, whether it's a point, a polygon. These could be things like the color, or the projection matrix, or the view matrix, or a texture map. Okay, so you have these three different kinds. So a simple shader program might look like this example. So let's take a look at a quick example of a shader program. And the first one we're going to do is a vertex shader. And so we have some constants, like a projection view matrix.
and a normal matrix. And then we have our attributes. So this is like our vertex position, our vertex normal. And then we have an output. We're going to send the normal out because we want to draw that as a color to the screen. And then we're going to write our main function, which we're going to do two things. First, we're going to multiply the normal matrix by the normal so we can send that to the fragment shader. And finally, we want to calculate the final position of this vertex using our projection view matrix times the A position. And then now we're going to do a fragment shader, which basically we're going to include the normal that we just passed in from the vertex shader, and then our main function. And all we're going to do is, because the frag color is a 4-component vector, we're going to wrap the 3-component v normal with a vec4. And essentially what this will do is allow us to visualize the normals for a 3D model. So, thank you for watching the video. Just as a quick summary, we covered vectors, we covered matrices, we covered transformations, so being able to do things to our points. We talked about the different components that you need in order to do WebGL. And lastly, we talked about shaders. So I want to thank you and hope to see you in the next video. Thank you.